So I'd like to give a little update on the physics problem that I posted, I guess it was a couple weeks ago now, at the time this video gets posted, where the enemy ship is trying to avoid a black hole somewhere in the center of the diagram here. And so there's going to be a distance within which, or range within which, the ship tries to go away from the black hole, and a distance, R2, outside of which the ship tries to go back to the black hole. And in between these two, it's safe for the ship to coast. I've decided to go with a little bit simpler approach, because now I've got the subroutine where the ship can head toward the next nearest black hole. So that kind of makes the coasting and coming back behavior not quite as crucial. Although if it were, say, a friendly ship or a ship that's trying to recover from the player chasing it, it might engage in this behavior solely and ignore the more aggressive behavior. But the issue I was running into, if you recall, is that I had these two equations, one involving the thrust and the speed at this point, R1, so when it enters coasting, and this other equation about the change in the velocity that involves both R1 and R2, but also this unknown V0. And so the issue was I had three unknowns but two equations, which leaves it unsolvable, meaning I need to pull something else out. But as I was working with the code to make the ship approach the next nearest black hole, I decided to change it up a little bit. So I'm no longer worrying too much about that first equation. This is now an alternative version that uses conservation of energy, basically setting the kinetic energy to be enough to overcome the potential energy that the black hole is causing for the ship. And so what I've got is a safety factor. So this is to make sure that it's got enough speed to avoid the black hole, because it can be doing things like heading toward the black hole instead of away from it. I'm thinking that's going to be on the order of 2. So, that could go as low as 1.5, as high as 3 or 4, depending on the aggro level of the ship. Then I've got the gravitational constants, a 2 from the kinetic energy, and a safety speed. And I realized what I needed was to have the speed be variable, not be a fixed V0 like we had up here. And so this safety speed can either be the ship's current speed, meaning the ship is approaching the black hole, it needs to not be approaching the black hole, so it needs to get around it. And so it could be the current speed, or it could be the fastest speed that the ship has. That's going to be the force of thrust divided by the damping coefficient. And again, these could vary. You could choose between the two based on the aggro level of the ship. But the reason I have both of those in there is because it allows me to fine-tune this R1 value, because this current speed is always going to be less than or equal to the terminal speed. That's why it's called terminal. And so this terminal speed actually gives the largest possible value that you can have here, and so it gives the smallest possible R1 that you can have. And you don't necessarily want it to be heading toward the smallest distance to the black hole, the closest distance to the black hole all the time. So that's why it would be nice to be able to vary this. So what I'd like to take a couple minutes to do today is to solve our mystery equation here for R2, because this leaves me with not knowing what R2 is. So I've already got this computed in the code. I've already got this set up as an option, so I just need to know what to put in the code as R2. I should also mention that I'm actually going to set this up as the minimum between, or excuse me, the maximum between this value and the size of the black hole. Size of black hole, meaning like its diameter, right? So each black hole has the circle collider on it, so this is going to be the diameter of the black hole. I've learned that this is often, in my testing, I've learned that this is oftentimes significantly bigger than this value is, which tells me that I can increase the mass to size ratio of my black holes, which will be exciting, make the game a little bit more challenging. So let's see here. So I've got this V0, we're now going to call that the safety speed. Safety speed plus, I've got 2gm over safety speed, 2gm over safety speed, which if I replace this with, now that it occurs to me, if I replace this with safety speed, this will actually simplify a little bit, because I'll have my 2gm here, canceling. Then I've got R2 inverse minus R1 inverse. And so R1 I'm treating as a known now because I have a way to calculate it. Equals B over M R2 minus R1. 2 minus R1. Cool. So now the goal is to solve for R2, which looks like a little bit of a mess because you got the R2 here and an R2 to the negative 1 here, but a little way I learned to visualize this is to always remember that this is a power difference of 2, which makes this a quadratic equation. And so if I take this whole thing and multiply it by R2, so everybody is going to get multiplied by R2. I have to do it to both sides of the equation, so that makes it legal. And then I would have an SS R2 plus a 2gm over SS, and now I'm going to break this thing up here because this R2 negative 1 is going to cancel with the R2 that I'm multiplying by. I have a minus 2gm over SS R1 to the negative 1 times R2, because this thing gains an R2 there. Oh, now it's occurring to me I don't plug this in for SS. I have SS term in here, my bad. So this actually, so this will cancel a little bit with something in the R1, I'm sure, yeah. And that needs to equal B over M. And here comes the square term. Here's where it becomes quadratic. R2 squared minus B over M R1 R2. Cool. I'm not worried about the R1 getting a negative 1 and a positive 1 power because it's a constant now, and it's R2 that I'm solving for. So in traditional quadratic fashion, let's get everybody on the same side. I like for my thing multiplying the square to be positive, so let's move everybody over to the right-hand side. So I'll have a 0 equals, so everything that has an R2 squared, which is just this term right here. So I'll have a B over M R2 squared plus I've got a couple things multiplying R2. So let's see, let's always put the positive things first. So I've got a 2gm over SS, I don't want to write it like that. There we go, 2gm over safety speed R1, because this thing is in the denominator. So that's got an R2 on it. This thing has an R2 on it, so minus safety speed. Where'd you go? There you are. And this guy's got an R2 on it, so minus BR1 over M. And that's all multiplying an R2. That was supposed to be an R2, not an unidentified R squared. Cool. And then everything that doesn't have an R2 on it. There was no such thing on this side. And on this side, that's going to be I'm going to get a negative 2gm over SS. So negative 2gm over SS. Cool. And so that take care of everybody. I've got 1, 2, 3, 4, 5 terms originally. I should still have 1, 2, 3, 4, 5 terms. Okay, cool. So going back to the quadratic equation, this thing is the thing that's multiplying R2 squared, so that's going to be our A. This long thing is multiplying R2 to the first power, so that's going to be our B. This whole thing isn't multiplying an R2, or if you will, it's multiplying an R2 to the 0th power, so that's going to be our C. And so all I have to do is put those as chunks into the code, and my R2 is going to be negative B plus or minus square root B squared minus 4AC divided by 2A. And that leaves us without really an issue. I'm fairly certain that we're going to need to select the positive root because this R2 should be a positive number because a negative absolute value of a distance doesn't make much sense. But what I'll do off camera is play around with some possible numbers for these. because we've got to make sure that the whole thing is greater than 0. And we've got to make sure that this thing doesn't become negative, because we shouldn't have a complex distance. So we also need to have b squared greater than 4ac. Although actually, this is not that difficult to guarantee, because as messy as this b is, right? I mean, this is a mess. This is going to be a bit of a mess to square. But whatever convoluted thing it comes out as, it's going to be positive, right? The b squared is going to be positive, and this part here is by default going to be positive because you don't have a negative damping coefficient, you don't have a negative mass, you can't have a negative thing squared. And then if you look at c, this thing is negative, but because all these things are going to be positive in here, the gravitational constant, the mass, the safety speed, they're all going to be positive. So this thing is overall going to be negative. So when you take 4ac, that's going to be a positive number. And so I actually don't need to worry about b squared being greater than 4ac. I need to get a better eraser setting on this thing. I don't have to worry about b squared being greater than 4ac. What I have to worry about is b squared minus 4ac being positive. And this thing is going to be positive, and this thing is going to give me a positive number added to it, right? Because this is going to be b squared plus 4a, and negative c is a positive, right? This thing will be positive, this thing will be positive, this thing will be positive. So that actually checks out. Cool. I wonder if we can get a similar argument going for the first condition here. Although now that I think about it, I don't just want this to be greater than 0. There's actually a tighter restriction on this. It needs to be greater than R1, because I need for R2 to be outside of R1, right? That's the whole point of solving this thing. So even if R2 were positive, if it were less than R1, it wouldn't do me a whole lot of good in terms of giving the ship directions. So let's take a look at that. So where do I have R1 appearing up here? I don't have it in A, I don't have it in C, but I do have it here in B term and in this thing. So at the front part here, this negative b, when I distribute the negative through here, I'll have this thing as a negative, this thing as a positive, and this thing as a positive. So this first part here is going to have a b over m times r1, because this negative in front of the big b term here is going to cancel out with this negative. And then I'm dividing it by 2a, because I can distribute the denominator like that. Divided by 2a, a is b over m. Cool, so these things will cancel. So that first term will give me a half of r1. So if I can just be guaranteed to get another half of r1 from somewhere in here, then I'll know that this thing is greater than R1. Again, trying to avoid actually having to square this thing would be nice. But one of the terms I'll get is squaring this piece. So I'll have a b squared over m squared R1 squared, not r to the 21st power r squared. Pen, give me the pen. There we go. R squared. And so then I'm adding stuff to that, because this thing will be positive, this thing will be positive. And so I'm only adding stuff to, I mean, I guess I'm technically taking away some of it from some of these cross terms. But this thing will, but this thing will be at least this much. And so this b over m cancels with the b over m down here. I have another half there. So yeah, this thing will get me an extra r1 squared, because that'll cancel with the thing on the bottom, and I'll have that over 2 after I square root. I know I'm doing horrible math here, trying to avoid doing real math. But yeah, this thing will become bigger than r1 every single time, I think. And I can always put in a check in the code to make sure that that works out. Okay, cool. So I've actually, as long as I make this thing the positive root, so I need to always select the positive root. Selecting the negative root would make this thing smaller. I always want it to be the bigger option. In fact, I don't want to select the negative root, because this thing under the square root, we just saw, is always going to be bigger than b squared. The thing under the square root is always going to be bigger than b squared, so this thing is always going to be bigger than b. And so this thing will get overrun by this. And so I need to select the positive root. Cool, so I've actually got my answer now. So for for R2, I just want to use this thing here. And I can put in a check. And if this thing ever doesn't work out to be bigger than R1, I could always just make it to be some multiple of R1. But I'm pretty sure that's going to work out. In fact, just to be safe, I'm going to put together, I'll do this off camera since it's a bit menial. I'll put together a code that tests a few numbers for these things just to make sure that this R2 always works out. So let me do that and I will be right back. Alright, I'm back. I have put together a little code that takes in all of the inputs that we need: the damping coefficient, the ship mass, gravitational constant, safety speed, black hole mass, the safety factor. I've gone ahead and had it calculate the R min using the calculation that I set up above here. So that takes care of that R min. And then it calculates the A, the B, and the C. So here's the A term, here's the longer B term, and here's the C term. And so what I've done is, rather than have the computer spit out errors about things, I've decided to just have it check all those various things that we were concerned about. So just in case I was wrong about this part, I've had it check for if b squared is less than 4ac, which actually, I guess, because we figured out that I need to check for whether b squared minus 4ac is less than 0, which shouldn't, that is the same thing, but just in case, we'll leave that as this form. And so then here we calculate the R max, and I'm going to go ahead and have it check the positive root and the negative root. And if both of those turn out to be negative, then we'll check for, then we'll say that there's negative R max. And then here we'll check for whether it works out to be bigger than R min, and here we're going to say R max works, and that deserves a little celebration. So how about a double exclamation mark there? So, and I've played around with a few different parameters on this thing. R max works for everybody being 1 and this one being 2. Let's suppose we really ramped up the damping coefficient. R max still works. Let's suppose we ramp it up really high, so there's a lot of damping. R max works. Then let's see if we make the ship supermassive. R max still works. Let's suppose we live in a universe with a higher gravitational force. R max still works. What about the safety speed? Let's say we're living a bit more dangerously. R max still works. Oops, that is not my backspace. Let's make this a bigger black hole. R max still works. And finally, let's suppose we're being super cautious with our safety. R max still works. Now, let's rework this thing to double check about the positive versus negative root. So let's see here. Let's change this one into a let's see, let's check. I guess I need to define both of these. So R max pos needs to equal the positive root. I don't want that thing there anymore. And then let's have R max neg, and then that'll take the negative root. So here we'll say if R max pos is greater than R max neg, then please print for me, take the positive root, else please print for me, take the negative root. Cool. And then we'll just say R max is equal to the maximum between those two, R max pos and R max negative. Yeah, that'll work. So let's see. Oops, invalid syntax. What did I do? Oh, whoops, I did need that parentheses. My bad. Save, F5, take the positive root. Okay, so now I know R max is going to work for everything I'm about to try. So let's make sure that we always take the positive root. Not that I'm doubting my math, but it's just nice to confirm it. Take the positive root, add a couple zeros here, take the positive root, add a couple zeros here, take the positive root, add a couple zeros here, positive root, one more. And it's kind of hard to imagine my code changing these by all these different orders of magnitude. I suppose I should try some different combinations as well. F5, take the positive root. Let's see, try that. Yeah, let's say, yeah, there we go. Take the positive root. Okay, so I'm pretty sure this is confirming that this is the one we should use. Again, I'll put a check for it in the code just to be safe. But otherwise, I think we're good to go. I think we've got this problem solved. I'll play around with this a little bit more off camera just to double check. I'll probably set up a bunch of nested loops to vary all of these parameters together. And I'll just have the code print out an error message if it turns out that it takes any of these paths that would be bad. So, like this is bad. And other than that, I think I've got this problem solved. Again, if I've missed something, if I messed up on the algebra there, or if I've missed a physical constraint, please let me know. But the next thing I'm going to do after I double check my numbers on this is implement this solution into the enemy ship controls. I'll run that as a test, and then next time I will show you the results, hopefully. Thanks so much for watching. I'll see you next time. Bye-bye.